If you look at the night sky carefully enough, you'll notice that different stars have a range of different colours. Beyond aesthetics, you might be wondering why astronomers actually care about what colour a star is though. And also, why we don't see any green stars. To understand this, it's time to watch this space.
3, 2, 1.
Stars.
Every object in the universe emits light. Mostly, this is in the non-visible parts of the spectrum though. For example, everything in this image is emitting in the infrared part of the spectrum, including the Leslie's cube, which is full of boiling water. GCSE physicists, you might know this because it's one of your required practicals. When we switch to viewing through our infrared camera, we can see that the side of the cube that's painted black is emitting the most infrared radiation. This is because black is the best colour for absorbing and emitting infrared light. It's also why black seats in a car will heat up more rapidly in direct sunlight, but also cool quicker when it starts to get dark. Astronomers and astrophysicists treat stars as black bodies. This means that they are assumed to emit light across the full electromagnetic spectrum, from low energy radio waves to the most energetic gamma rays. They are not equally bright across all wavelengths though, with their peak brightness depending on the surface temperature of the star. If we look at the intensity of light emitted compared to the wavelength of light, this will hopefully make more sense, with this graph generator from the PhET simulations available from the University of Colorado. A blackbody with a similar temperature to us would see its light curve peak in the infrared part of the spectrum. But as we heat it up, the light it gives off will become higher energy. This means a greater frequency and lower wavelength. This is why if you heat up a metal block, it will become red hot. Heat it further and it may become white hot. And if it didn't melt and you could heat it far enough, you could even get it to become blue hot. So, if we see a red star in the sky, that means it has a generally cooler surface temperature, usually less than 3,500 Kelvin. Our sun is hotter than this though, at around 5,800 Kelvin, which is why it appears yellow-white. To appear blue hot, you're looking at surface temperatures in the 10 to 50,000 Kelvin range, even though this actually means peaking in the ultraviolet parts of the spectrum. A-level physics students, if you're on the AQA specification and taking the astrophysics option module, then there is a way we can quantify this, Wien's law. Here, lambda max represents the wavelength of light at the peak intensity on our blackbody curve, and T represents the surface temperature of the star. 2.9 times 10 to the minus 3 is just a constant, and weirdly, mK are units, meter Kelvin, which makes this unlike pretty much any other equation you study at A-level, and yes, it is in the formula book, don't worry. So, if you can analyse the brightness of light that a star emits across the spectrum, then you can work out just how hot its surface is, regardless of how far away the star might be, how long the light took to reach us, or how we'll probably never get to visit more than 99% of these stars at any point in humanity's future. But why aren't any of them green? If we look back at the graph of intensity versus wavelength, where stars would peak in the green part of the spectrum, they're also very bright across the rest of the spectrum too. You may well know that white light is essentially a combination of all the colours within visible light, so for stars that peak in the green part of the spectrum, when we see the range of colours it actually emits, then our eyes can't see the individual colours separate from each other, and it just appears white to us. But what is the point of all this? Why would we care about working out the surface temperature of a star? Unless we can do something with it, it seems like a fairly pointless task. Thankfully, it does have a really important use for astrophysicists, otherwise I probably wouldn't have steered the script for this video in this direction. That use is in working out the power output otherwise known as the luminosity of the star. Looking back at the overall curves for black bodies at different temperatures, you can see that not only do hotter stars have a lower wavelength for their peak temperature, but the entire curve for the intensity of light is higher. The other factor we have to consider when thinking about the power output of a star is its size. If you imagine two stars with the same colour but different masses, then maintaining the same surface temperature on the largest star will require more nuclear fusion in its core per second, meaning that it will have to have a higher luminosity. Put all this together and you get Stefan's law. This links the luminosity, or power output of the star, to the surface area, surface temperature, and Stefan's constant, which is 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4. This version is in AQA's A-level formula booklet, as is Stefan's constant, but this version makes use of the fact that the surface area of a sphere is 4 pi r squared, and is probably the more useful version of the equation. As regular viewers might know, I don't usually go into exams tip mode, but if I were an examiner for AQA, then one of the things I might be looking at giving students is the power and the peak wavelength, so that they had to use Wien's law to work out the surface temperature, and then the radius version of Stefan's law to work out the radius of the star. But there are probably a good chunk of the audience that aren't really thinking of exams and are instead wondering how we actually calculate the power output of a star, given that it's going to be incredibly difficult to work out the radius from direct observations from Earth. For this, we can use the observed intensity of the star from Earth to work out its luminosity. In this equation, r is not the radius of the star, but is instead the distance between you and the star. As if this double use of r for different things wasn't bad enough, this equation isn't in the formula booklet. Some of us might also be thinking, what is the point of all this? Well, from the luminosity of a star and its surface temperature, we can work out what stage it is at in its life cycle, and what its evolution is likely to look like based on its current situation. If you want to look at how that works, then search up spectral class and Hertzsprung-Russell diagrams. We will likely dedicate a future episode to this, but for now, we're going to call time on our second series of Watch This Space. Whilst I'm not going to reveal the topic for our third series, what I can say is that I need to get back to model making through the spring term. In the meantime, we're going to cover some more general topics and questions from the comments, including a special video next week with tips for anyone hoping to get started on observing the skies for themselves. Thank you to everyone who's watched this second series of Watch This Space. Extra thanks to our subscribers, those who've got involved in the comment section and hit that like button along the way. If you've got a spare few minutes, why not check out this video from us too? Until next time, please continue to watch this space. Thank you.